Yes,
Beautiful.
very good. Okay, so the next speaker, Valenti from Frankfurt, will speak on exotic phases in Honeycomb and Kagome lattices and the power of material design. So very, very immediately topical.
So thank you very much, Dan, for the introduction. And I would like to thank Rajiv and Piers for the kind invitation to present some of our results. And in fact, the discussion now, it's a very good introduction to some of the topics I would like to talk today. So what I would like to discuss in this talk is some strategies that we have been following in recent years to theoretically describe and predict quantum materials with exotic properties. And as example, I will focus today on Honeycomb and Kagome lattice-based materials, which are presently being intensively studied for manifesting a large variety of topological phases that I will be describing along the talk. First of all, I would like to acknowledge my collaborators in this work. So my group in Frankfurt, Thomas, Sananda, Francesco, Shinivali, and Paul, as well as Steve Winter, who was a former postdoc in Frankfurt and is now at Wake Forest, and Johannes Knoll and Valentin Lieb from the Technical University in Munich. So to set the stage for a macroscopic description of an interacting electronic system, we can do a minimal description in terms of 4 energy terms, which I have classified here in terms of single particle versus multi-particle and single orbital versus multi-orbital. And these are the kinetic energy, the spin-orbit coupling, the Coulomb repulsion, and the Hund's coupling. And depending on the strength of these interactions that I can represent in terms of these from weak to strong, we can in principle classify the material classes that we know as a function of the strength of the interactions, going from the strongly correlated cuprates up to the iridates, where we are dealing with 5D electrons. And therefore here we have a competition between these 4 interaction terms. So now what I would like to do in this talk, based on these 4 interactions that I just introduced, is to split the talk into 2 parts. So in the first part, I would like to concentrate on itinerant electronic systems, so weakly correlated systems, and concentrate on topological phases in these systems. And I'm going to indeed present some materials like the very much discussed Kagome metals and of course graphene. And in the second part, I will then go into the opposite limit, so the strongly correlated limit when we are in this regime of these 4 interactions. And this corresponds to Mott insulators and frustrated magnets, if we are considering now these underlying lattices. And then I will be talking about systems like Herbert-Schmidtite or the Kitaev material candidates. And if I have time at the end, I would also like to discuss about, for instance, unconventional superconductivity when we start to mix between these 2 types of materials. So what do we do in order to investigate the properties that we want to investigate in these materials? So in fact, there is a big step of writing down an interacting Hamiltonian as the one I was showing to you and obtaining the material specific properties. So the way we follow are by considering 2 strategies. So one is to solve the Schrödinger or the Dirac equation by, so computationally, by making use of combination of density functional theory and various many-body methods, so that we can take care of correlations. And in fact, it was now discussed that as soon as we are computing with many-body methods, the calculations become rather complex. And that's why we need big computer power in order to proceed with these type of calculations. But the other type of strategy that we are also recently following is indeed, which was also in the discussion today, to consider statistical learning of unbiased data sets. And I will show some examples on what I mean by that in the next slides. So let me start first by considering now itinerant electrons. So I am in the weak coupling limit, and I'm going to concentrate on the properties of these lattices. And in fact, that already at the level of a very simple nearest neighbor tight binding Hamiltonian describing these lattices, we know that we have a very rich band structure as the ones showed here for the Honeycomb lattice and for the Kagome lattice, where these band structures show a few interesting features that promote topological phases like Dirac points, Banhof singularities, or flat bands. So, and this is in fact in band topology one makes use of in order to predict many topological phases in these materials, in let's say weakly correlated materials. But what I want to do now here is, instead of focusing on a specific material and extracting what topological phases we may expect for these materials, I want to do the reverse. So I want to choose a topological phase that I would like to have it realize, and then find out which restrictions I should impose on the material in order to have this phase realized. So this, considering this as a route for designing materials with tailored properties, with a certain phase that I want to have realized. And the way that I would like to do that, and I'm going to do that, is by employing statistical learning of unbiased data sets. So what is that? So what we want to do is to engineer topological phases based on a statistical analysis of data. And as a proof of concept to show how this works, I want to show the following example. So I want to show you by a statistical analysis that in fact the Haldane model is the prototypical topological model on the Honeycomb lattice. What I mean by that is that if I want to have in a material the realization of a Chern insulator, so of course the Haldane model is defined for a system that has broken time reversal symmetry. So if I want to have the realization of a Chern insulator in a material, what I need to have is nearest neighbor hoppings that are real and next nearest neighbor hoppings that are complex. And any other type of term that you may put into there is not really relevant for getting this Chern insulator. So in order to show you this, that's how I'm going now to introduce this statistical learning. So how does it work? So first, what we do is we model the lattice that we are interested in. So here it's the Honeycomb lattice, and we model it through a set of on-site and tight binding parameters that can go up to a certain neighbor. And in principle, we take complex numbers. And then starting from a physical origin, we sample a set of hopping parameters randomly in a region around this initial point. And now, given these random configurations, what we do is we compute the topological invariant of the phase we are interested in. So for instance, if I am interested in a Chern insulator, what I'm going to calculate is the Chern number for each one of these random samples that I have created. And this is in fact a calculation which is very fast. In fact, the way of calculating the Chern number is by using, for instance, the Fukui formula. And once we have all these sets, so 10 to the 6 random sets of parameters, the question is what we do with that. So now we have really a lot of parameters that are labeled through this Chern number, and now we have to take the physics out of that. So how do we do that? So in principle, we should start by calculating correlation functions. So in fact, joint probability densities between these different parameters. However, if we look at the dimensions of this type of calculations, so indeed what we would like to do is to map, to do a mapping of a d-dimensional complex vector into a real number. And now if we think, for instance, if we are having samples that have up to next nearest neighbors tight binding parameters, we are having a dimension of 10. And if we want to do good statistics, we need of the order of 10 to the 6, 10 to the 8 samples. So in fact, we have, exponential scaling. So this is not possible to do this type of calculation. However, what we found out, and this is by learning from statistical physics, in fact, is that already at the level of marginal distributions, and the marginal distribution for a given parameter consists on basically integrating out all other parameters except this one. So already at the level of marginal distributions, we can get a lot of information about this set of samples that we have created. And these are the typical marginal distributions for the various parameters that one can find for the different labels that here are our Chern numbers. So now how do we get the results? How do we get the physics out of that? So what we need now is to define the importance of the parameters. So we need a contrast in the signal. So basically, which parameters are important for a given phase and which are not. And the way to that we are doing that is by defining the Bhattacharya distance, which is a definition of a distance between these marginal distribution functions, which is positive if the distribution functions are different, and it increases the more different that these distribution functions are. So it means that this type of distance gives us information about the relevance of certain parameters with respect to the others. And this is the type of result that you get out of this analysis. And basically, if you observe here, what we have is that the most important parameters to describe this type of Chern phases, so Chern number plus 1 or minus 1, it's basically the on-site term, these nearest neighbor real tight binding parameters, as well as the phase, maybe we see that better here, as well as the phase of the second neighbor's hopping parameters. And all of the parameters, and you can, I mean, we have done a lot of samplings, all of the parameters are irrelevant. So therefore, this is a method that gives us, starts from random sets of parameters and gives us, by just using these statistics concepts, gives us information about a physical phase. So now,
could you say what X was again in this distribution?
Oh, this X is here. Oh, sorry, here. This is the X. So basically it defines this set of parameters. So the X corresponds to, when I do this marginal distribution function, it corresponds to one of these parameters. So for instance, this X would be in this case here, the marginal distribution of the mass term, of the nearest, of the real part of the nearest neighbors term, etc., etc. Okay. That's this X.
Thanks.
Which, yeah. So now I'm going to use that for investigating these materials, these Kagome metals that are being very much intensively discussed, all 21. In fact, there was a lot of work reporting interesting results about these materials. So I would like to use this type of method in order to investigate topological phases in these materials. So what do we know about these materials? So these materials, the first report that I know of these materials is from Santa Barbara, where they were able to synthesize Kagome lattices of vanadium, which are separated by layers of antimony, which form honeycomb lattices. This, and what is important in this material is indeed these vanadium Kagome layers, where we have a filling of 1 electron per 3 vanadium. So maybe let's look at here on this perspective. Now, what we know about this system is that the system is metallic. It shows a Pauli paramagnetism at high temperatures. If we look at the band structure of this system at high temperatures, when still no phase transition happened, here on the right is shown the band structure where only the vanadium bands are plotted. And we see here these features that we know from Kagome lattices, that we have all these Van Hoff singularities. But what is important about this material is that the Fermi level, so this type of filling, is precisely at a Van Hoff singularity. And this already is telling us that this is an instability in the system. So we are going to expect at some critical temperature, some phase transition in order to get rid of this type of instability. And this is indeed what happens at about 80 Kelvin. There is a transition into a charge density wave phase. So the system, in fact, distorts into superlattice, which has it's a 2x2 Kagome superlattice. And going further down in temperature, the system becomes superconductor. And a lot of discussion is going on the nature of this charge density wave, as well as the nature of the superconducting phase. So especially what I would like to concentrate is on the charge density wave. Since there has been now a few reports about the fact that these charge density waves seem to be chiral. So basically they seem to break time reversal symmetry. And here what I'm showing is an illustration of scanning tunneling microscopy by Yang and collaborators, where they observe this handness on the distribution, on the electronic distribution along this charge density wave. So what we want to do now is to try to find out in this type of Kagome lattices. So let me go here. We are in our Kagome lattice. So when we go into this 2x2 into the super lattice, what kind of charge density waves we may expect if we are in this underlying lattice, especially when we put ourselves at this filling, which is a filling where we are exactly at the Van Hoff singularity of the undistorted lattice. So we use now this method that I was introducing to you. This is statistical learning. We call it statistical learning. So by basically taking a reference point, generating random number with a random number generating all these samples, and then analyzing the data set. And here, for instance, if we include or consider some symmetry, this reduces the number of parameters that we may take in this analysis. And I want to show you some results, for instance, by constraining ourselves to C6 symmetry. And the type of phases that one finds out is that we can have trivial phases, topologically trivial phases, like the Star of David or the inverse Star of David. And the strength of these plots, it means that for the realization of such a phase, it means that we have very strong neighbors along these connections here and less strong along these connections here. But we also have realizations of Chern insulators with Chern number 1 and -1, which are chiral. So the mirror symmetry is broken, time reversal symmetry is broken, but the product of the two is preserved. And again, the information that we get from this analysis is what kind of parameters, so in fact, going now to these hopping parameters, what kind of parameters are the ones that are going to realize this type of phase, which has this type of chirality. And there are also some phases which are higher order. So if we compare with the experiments with what we know from experiment for these vanadium Kagome metals, in fact, what we find is that some of the phases that seem to be reported correspond to these C1, C-1 phases. Now, one, of course, can do this game by reducing the symmetry. Then, of course, we have more parameters. So if we break the C6 symmetry and we go into the C2 symmetry, which has also been discussed experimentally to be observed, that then what we find out is that this type of higher order Chern insulators are fragile and the ones that survive are those. So with this type of calculations, one can get information about where should I look for a certain topological phases, which are the basically the restrictions that I have in my material, and therefore I could start designing or modifying materials to go into this region where we are supposed to find these phases. And we check that with the Kagome metals. So this is work in progress. And now let me go to the second part of my talk. Hopefully I'm fine with time. Okay, so, and the second part of my talk, I want to go now to really the strongly correlated limit. So I'm going to consider, again, these underlying lattices, but in the limit where I have mod insulators. And because of these underlying lattices, I can have, in fact, magnetic frustration. So for the case of the Kagome lattice, because of per construction of the lattice, so if basically we consider that we have now our localized magnetic moments, that they are antiferromagnetically coupled, then of course we see that we have straight away a geometric frustration. So the third spin doesn't know how to align with the other two. And indeed the Kagome lattice is the most frustrated lattice that we know of. So therefore, this is one, in fact, one type of system that is very much studied because of the manifestation of this geometric frustration. But there is another way of creating frustration, magnetic frustration in the system. And this is by doing Hamiltonian engineering. What do we mean by that? So basically by writing up Hamiltonians, so spin Hamiltonians, that consists only of non-commuting terms. And because they consist of non-commuting terms, we are going to have a strongly magnetic frustration. And one model that has been very much discussed in the last years, and it's still very much discussed, is the Kitaev model. So the Kitaev model, a precursor of the Kitaev model, is the compass model. And this model, I'm going to introduce it in a moment, but the audience knows the model very well. But we will see that, again, this model is highly frustrated. And because of frustration, the same as for the geometric frustration, there is, in fact, no long-range order. And we then have the possibility to have a realization of a very elusive type of state. So this is one of the most, well, one of the very much sought of states, which is the quantum spin liquid. So the quantum spin liquid, so if we want to define what is a quantum spin liquid, in fact, Phil Anderson was one of the first to think about this concept of promoting quantum fluctuations and therefore having non-ordered states, and basically introducing this concept of valence bond. So the way we can define a quantum spin liquid, this is a cooperative quantum state with fluctuating spins down to lowest temperature and without symmetry breaking. The ground state is long-range entangled, and what is even more interesting about these quantum spin liquids is the nature of the excitations, which is fractionalized. Like, for instance, the case here of the spinon, which is a particle with spin and no charge. So that lives in this sea of valence bond. And why, as you know very well, why one is very much interested in getting these materials, these quantum spin liquids, as well as the corresponding fractionalized excitations. So this is in the direction of building up topological quantum computers, as was suggested by Alexei Kitaev, basically by building qubits through these fractionalized excitations that will allow then operations which are protected by topology. So the question is, where do we find these materials with these fractionalized excitations? So if we consider first the case of geometric frustration in the Kagome lattice, so Herbert-Schmittite is one of the candidate materials for a spin liquid. So it's built of these perfect Kagome lattices of copper spin 1/2. This is a Mott insulator. And in elastic Newton scattering experiments here, for instance, show a diffuse excitation spectrum, and the system doesn't order up to low temperatures. So it has been proposed to, in fact, that this system is a spin liquid. However, one has to also, and this is all wasn't the discussion previously, one has to be very careful about the materials, because there are issues about anti-side disorder and many other issues that could spoil the true intrinsic nature of having a spin liquid. So these is issues that are very intensively discussed in this material. So let me go now to the Kitaev materials, where in fact the Kitaev materials are interesting because our starting point is a model where we know exactly all the properties of the model, and it has the properties that we would like to have. And this is what we nowadays know as the Kitaev model. So in fact, what Kitaev did is to solve the model exactly. So this is a model which it is a nearest neighbor bond-dependent Ising model on the honeycomb lattice. And because of this bond dependence, we can see that it is strongly frustrated, because if we place ourselves in one point in the lattice, the spin of this one point or this one side has to interact with the Z interaction with this neighbor, with the Z component with this neighbor, and with the S component with this neighbor, since the three components of the spin don't commute. So this is a highly frustrated model. So let's say Kitaev solved it exactly by using the representation of Majorana fermions. The ground state is a C2 spin liquid, and the excitations are gapless Majorana fermions and static gap fluxes. So beautiful physics. The question is, can we get that into material realization? And this, in fact, this is a very nice work by George Ackley and Guignat Kaliulin, where they were the first ones to really propose a recipe to have a realization of this model on material. So when we write the Hamiltonian in the usual way, the spin Hamiltonian in the usual way we're used to, by including the Heisenberg term, the Jałodziński-Moria term, and then this symmetric tensor term, in fact, realization of the Kitaev model corresponds on getting all these terms zero and only having this one term surviving, and it has to be bond dependent. So the diagonal has to be bond dependent. So the recipe by George and Guignat was done for D5 transition metal ions with a strong spin orbit coupling. We need that because we need these bond dependent interactions. And in fact, with a crystal field splitting, which is octahedral, so that we can work with the T2G orbitals with the D5 filling. So then we have the splitting into the field J effective 3/2, and we are at the end of the day with J effective 1/2. If we have a strong Coulomb repulsion, then these are our localized pseudo spins that then we bring together into these honeycomb lattices in a way that all these interactions can be suppressed. And the only interaction that survives is indeed this interaction here, which can be described in a following process. So this is an interaction where we have 1/2 interaction through the 3/2 orbitals. In fact, the plus minus 3/2 orbital. So that therefore this is an Ising interaction, and the coupling is directly dependent on the Hund's coupling. So this is, in fact, the Kitaev interaction is an interaction which has its nature on the multi-orbital character of these systems. So there has been a lot of work, experimental and theory, trying to find out materials to realize this physics. And these are some example of them. One of so the alpha ruthenium trichloride, as well as the 213 iridates, the 2-dimensional and also the 3-dimensional versions. And one of the most studied material, and we will have today and tomorrow more talks about these Kitaev systems. This one especially is alpha ruthenium trichloride. Now the point is, these materials are not perfect. Therefore, even though the strongest interaction is a Kitaev interaction, there are also other terms which in fact prevent these systems to show a spin liquid phase. So in fact, all these materials order one of the orderings they show, so let me concentrate on alpha ruthenium trichloride, is a zigzag magnetic order. And this is due to the presence of these other interactions, not only a small Heisenberg interaction, but also other off-diagonal anisotropic interactions. So nevertheless, even though these systems order, and these are typical values of these coupling constants, these systems show very interesting phenomena, so excitations. And here, for instance, I'm showing one of the first experiments on alpha ruthenium trichloride, so neutron scattering experiments by Steve Nagla and his group, where they were measuring, in fact, alpha ruthenium trichloride in the ordered phase. So you can see here around gamma this very nice magnon, but there is all this continua of excitations, which is a consequence of the fact that there are all these anisotropic interactions. And there has been a lot of discussion about the nature of this continua, whether this is still one has some Majorana excitation type here surviving, or what it is. So I'm not going to do a review of all the experiments. There are many and many nice experiments, but there is one experiment, and this is an experiment that I think it will come in the later today in the various talks, because this experiment is very special for the prediction that it gives, which is thermal Hall conductivity under a magnetic field. So in fact, if you take the Kitaev, the purely Kitaev model, and you put it on the magnetic field, and this was already done by Kitaev, then what you expect is that you are going to have a chiral spin liquid state. So, and also this was done by Kitaev. He then calculated the thermal Hall conductivity and predicted that the thermal Hall conductivity in this chiral spin liquid state should be quantized. And these are experiments by Yuji Matsuda and collaborators from 2018, where they did these measurements of thermal Hall conductivity. Here, what I'm showing is measurements for magnetic fields along the A direction and the B direction. And they observed a quantization precisely at the quantization value that was predicted by Kitaev. And there is a lot of discussion about this thermal Hall conductivity. I will leave the discussion for the next talks. Maybe just to mention that if we look at thermodynamics measurements, so for instance, here the Gruneisen parameter, which is very sensitive to phase transition. So this is a Gruneisen parameter as a function, so magnetic field dependent Gruneisen parameter. Then what one observes, these are measurements by Philip Gegenbart and collaborators, where we did also some calculations. So if we put ourselves in this direction, along the A direction where this quantization has been seen, so thermodynamics don't seem to see this, this phase transition. So thermodynamics sees the phase transition when magnetic order is suppressed. Here there is a second magnetic phase transition, which has also been observed in neutron scattering experiments between two different orders. But there is the thermodynamic indication of this, of what I was showing here seems very difficult to see if this phase is there. So I think this is an issue of discussion, and we can maybe discuss that later on. But what I want to do, I don't know my time. How am I doing with my time? Do I have 5 minutes, or it's over my time?
It's just a question of how much questions you actually want to have. It's the same.
Okay, so maybe I just wanted to say that maybe just my last 2 slides is that there is another way to manipulate this system, and it is by strain. And this is what we have been pursuing together with experimental colleagues to make heterostructures of alpha ruthenium trichloride with graphene, because what we are doing with this type of heterostructures, one is straining alpha ruthenium trichloride, and these are basically the electronic structure calculations. So you have a charge transfer from the graphene, you hold up the graphene and you electron dope alpha ruthenium trichloride. And basically what one observes is that you are building this type of electronic states. And indeed, what you are changing your alpha ruthenium trichloride so that you are sort of killing these interactions that you didn't like. So the Kitaev interactions are promoted. And maybe this is a route to follow. So maybe just skipping that, it's a route to follow to also consider heterostructures. So here it's my last slide. Heterostructures of these mod insulators, of these Kitaev materials, now with, for instance, here with graphene, which corresponds to this side of basically of the left side. So, and here is my concluding slide, where I wanted to show to you different ways of describing topological phases in itinerant systems and in strong correlated systems. And I thank you for your attention.
Hey, thank you.
Maybe.
So, Piers, do we now have time for questions?
Yeah, no, you have plenty of time for questions. The schedule says till 15:15.
Yeah. Okay. Well, all right. So now we are open for questions. All right. Shuvik, I think you're first in line.
Yeah. Hi, Rosa. It was a nice talk.
Thank you.
So my question is about the Kagome part of the talk, the Kagome metal part. Mm-hmm. So in this method that you outlined, the numerical method, so is it optimizing towards constructing mean field Hamiltonians with desired topological properties?
Well, okay, not necessarily. In fact, what I showed to you, I applied first to tight binding models. But what I took is that my tight binding parameters are complex. And in principle, where you get this tight binding model from, so the origin of these, let's say, hopping parameters, you can then go back to the material and say, okay, this should be the chemistry that brings me to this hopping parameter. So at this level, I didn't include correlations yet. This is the next step we have to do. So if you want, one can talk in this language that I am still at the level of mean field, in the sense that I didn't include explicitly correlations. I only include kinetic energy, and I included spin orbit coupling. These were now the parameters that I was considering. But the next step is indeed to include then the correlation.
Thank you.
Nick, I think you're up next.
Yeah, so I wanted to ask about the alpha ruthenium chloride on the graphene. Is the strain in that case, is it a uniform in plane, or is there a direction that it picks out? Or
okay, thank you, because then I can't show what I just jumped. So let me. I thought I was really running out of time. So okay, so this is your question, right? So in fact, what we do when we do these calculations, we let the whole system relax, and basically what we find is that it's rather uniform. So what in the experiment, it's basically flakes. They have flakes of alpha ruthenium trichloride on graphene, and the most important question is, how do you orient? So the orientation of these flakes. And what we did is we tried many different orientations. So which is the best way that the systems like to orient? And by doing, so this is with DFT relaxations, which is the one that gives you more stability. And we found this type of orientations. And then we were comparing, in order to be sure that this has something to do with the experiment. So each orientation gives you different strains. So we were comparing with, for instance, Ken Birch, to look into, they had done some measurements to look, in fact, whether they were seeing some tensile strain or compressive strain, which is related, in fact, to how I orient. So this is, in fact, the type of what you have to worry about is the orientation of graphene and with respect to alpha ruthenium trichloride. If you're asking about the fact that graphene, it has this modulation is much larger than at this level that we are talking about.
So the strain doesn't somehow favor one of the Kitaev interactions, or they all, I mean.
The strain, okay, we have a little bit of anisotropy, this is true. So it, I don't have the numbers here, but it basically enhances Kitaev. It reduces the gamma, what we call the gamma term. And it's true that we get some distorted. So there is a small distortion. So the honeycomb lattice of alpha ruthenium trichloride is not anymore perfect. There is some distortion, which this translates into that you have, let's say, the Kx is not exactly the same as Ky and Kz. That's indeed the case. Yeah.
Okay, Hayoung.
Okay, thank you, Roger. I just have a follow-up question to your Kagome model, where
Yes.
the question about the statistical averaging about the tight binding model.
Mm-hmm.
So, I mean, I first of all don't get quite what's the purpose of doing it, and because you can construct the tight binding without going through that, but then you said that. I mean, yeah, I mean, it's a large unit cell and so on, so it's not that simple. But if you want to focus on some of the Van Hoff singularities and so on, one can probably get them. But then I thought that you will add some effect of the Coulomb interaction. I mean, they're basically some Hubbard interactions or something to see how statistics will help you to understand which charge density wave will preferred.
Yes, this is what we're doing now. But the point is that this is not just constructing a tight binding model, because what we do here is we have a set of random T's. Usually when you construct a tight binding model, you take, let's say, nearest neighbors and the same values of nearest neighbors, et cetera, et cetera. Here I was showing a case, but you have a set of parameters, completely random parameters. And with this method, basically, you can extract what restrictions you have in your parameters to obtain certain phases. So if we do it by constructing I sit down and construct the tight binding parameters, the question is whether I'm going to find all possible phases. I'm
sorry, what do you mean by all possible phases?
You mean
possible phases, numbers? Different numbers?
No, all possible phases that you can realize on your lattice.
Binding. Sorry, I'm really confused because you're dealing with a tight binding without broken symmetry. So my tight binding model will respect the symmetry of the lattice.
Yes, in the example that I gave, yes. So I gave you a C6 symmetry, but in principle I could, and I showed you, and I gave you a 2x2 lattice. We could do it a larger lattice. And my point is that with this method, you get all possible, so you basically exhaust the possible realizations of phases that you can have when you are in this 2x2 or in this 4x4 lattice. That's the point.
So when you say possible phases, are the phases with the different Chern numbers, because these are just
exactly this is my label.
Problem.
Yes, this is my label. So I just labeled with the Chern number. I could have done the C2 number, or I could now go and do the next step, include interactions, and define a new label that defines my phase.
Okay, exactly. So you're not yet the charge density way where you don't break the symmetry.
Yes, yes,
non-interacting problem without the broken
No. What I'm not giving you is the reason of the reason why this charge density wave is happening.
That's what I like.
This is the part I don't have. What I'm saying is this charge density wave should be realized, which is the origin of this charge density wave. This is something that, of course, the statistics won't give me, but they give me, I can realize this charge density wave. So it's a second calculation where then I have to go to first principles. If I want to find out why I have this charge density wave happening with these parameters. Where could that come from? Is it an electron-phonon interaction, or is it an electron-electron interaction? This is the next step.
Okay. Got it. Okay. Thank you.
Rajiv, I think you were next.
Yeah, I was very nice talk, Rosa. Yeah,
Thank
I was
you.
going to ask about also about the Kagome metal piece and your statistical analysis. You had this distribution which you called the distance between distributions defined by this Bhattacharya distance. Why did you pick that one? There are other distances between distributions that are more popular, like Kullback-Leibler and others.
Yes.
Is there a reason to pick this one?
Yes, we tried a few different distances, in fact, and we found that this one was the one that was, in fact, making the distinction, because we need to make a distinction between the parameters. We need to make a hierarchy of the parameters, and this one we found was the most effective. We tried many. You are right that people use a lot other distances, especially when you are thinking about clustering of your data. So there are others that are more suitable. But for this type of analysis, we realized that this was, for us, the most useful. But yes, thank you. It's interesting when one digs into this field of statistical mathematics, that there is a lot that has been done. And this was for us the one that was more effective.
Henri?
I don't know what happened. I was disconnected for a while, so I missed some. I was wondering the situation in the Kagome case, in the Kagome metallic case.
Yes.
Obviously, from what I have seen on the published experiments, this system seems to be weakly correlated. There are very, very few indications of the importance of correlations. So would you agree with that on the theory side?
Well, I mean, I treated it here as weakly correlated in the sense that basically for me, correlations were not really the key factor, but there is a lot of discussion, these chiral charge density waves, whether they come from electron-electron interaction, so nearest neighbor electron-electron interaction, or it's a consequence of the electron-phonon interaction, so the fact of the electron lattice. There is a lot of discussion, which is the reason for that. If it were electron-electron interaction, then you have to worry about indeed including this interaction. But I think that we are still not there to say this yes and this not. But these are the two mechanisms. So electron-phonon, we wouldn't require to have strong correlations. But if it is an electron-electron type of mechanism, an electronic mechanism, then you need to include this type of interaction. So that's the situation that I know so far. It could well be that that maybe we will know more the more experiments that are around.
Okay, but there is no sign of high magnetism. But I have the counter example of the system on which I am working, which is the sodium cobaltate, which has a very specific.
Indeed, the triangular lattice, right?
Yeah, it's a triangular lattice, but which is for a given concentration of sodium is Kagome. And in that case, we have strong magnetic effects, which appear a large enhancement of the temperature dependence of the susceptibility. We see the big differences between the carriers, and the carriers are certainly showing correlation effects. Okay,
no, but good point, Henri, because here indeed there is no observation of local magnetic moments. I mean, it's Pauli paramagnetism, what has been up to now observed. The system is metallic, Pauli paramagnetism. So we are not really in this region of localized magnetism.
Yeah, the difference is our system is an oxide, so you have some reasons to get more correlations, and we need the correlations to induce the Kagome. I'll briefly show that tomorrow, maybe.
Okay.
All right, maybe Zilka, the last question goes to you.
Okay, thank you. Yeah, so I think there are some experimental works, like from Joseph Cikalski, who shows that in some of the Kagome metals, the flat band forms, at least in sort of relatively sizable portion of the Brillouin zone, and others, I think theorists sort of have treated the destructive interference as if electrons localize on the little triangles and treat it with Kondo models. So I think there's a lot going on which says that there might be, in fact, very strong correlations going on.
But Silka, this is it depends very much on the feeling. What you are talking is about materials where you are really at so if you are really at the flat band. So you are these types of feelings, and then I 100% agree with you. You are really
okay. So you were not looking at that situation.
No. I'm here.
Okay.
I'm really here.
Sorry.
Yeah. No problem.
I see. Okay.
Maybe precisely our cobaltates are in that situation.
Okay.
All right, Piers, did you have anything to add before the lunch break?
No, I think this was a delightful talk and a great discussion that came afterwards. We really had a great morning session. And I think we'll now break for quote unquote lunch.
For lunch, for dinner.
Or for you, midnight snack, Henri. And we will rejoin again at 2 o'clock, I guess, to hear Puan Ong give his talk on Kitaev magnets, on alpha ruthenium trichloride. Should be a very interesting afternoon. So see you all back here at 2 o'clock California time.
Okay.
Bye-bye.
Bye-bye.
Bye.
We go for lunch.
Yeah.
For dinner.